Hello friends, welcome to my Pessimistic Guide to Anti-Aging Research, Episode 3, titled Curse of Proxies. The grand purpose of great science, called biology, is a study of all forms of life. In contrast, the whole purpose of different branches of translational biology, the one that aims to bring discoveries from the bench to the bedside, is us, and only us, human beings. The main objective is to find cures for various diseases and, naturally, aging. Clearly, we cannot subject human beings to raw experimentations, and the only seemingly viable alternative is to utilize animals. It is assumed that because model animals are in many ways comparable to humans, they can serve as adequate proxies for studying diseases and testing potential cures. Pilot clinical trials are permitted only after comprehensive animal experiments that produced unambiguously convincing results. According to the Nuremberg Code, animal studies utilizing at least 2 species are required by United States law prior to human trials. It seems sensible, logical, necessary. But apparently it's not enough, because most pilot clinical trials fail, and some even end up in disaster. A classic example is an anti-inflammatory drug, TGN-1412, that was comprehensively tested in 2 species, including monkeys, before going to a preclinical trial stage. However, the volunteers injected with this drug suffered from catastrophic failures of multiple organs within minutes after injection. Overall, the success rate for treatments in phase 1 clinical testing is estimated to be just around 8%. 8%, even though in animal experiments everything worked just fine. Why is that? Well, there are many possible explanations. For one, it could be a subconscious bias of researchers when they analyze experimental data. When one spends so much time and energy working on the idea, it is possible that the brain starts to filter out undesirable results, especially when it is directly connected to funding and therefore livelihood. Another possibility is setting experiments in such a way as to increase the likelihood of success. Many animal experiments recreate a human condition in question in exaggerated or simplified manner. For example, if you restore telomeres in mice that have critically short telomeres to begin with, you have every reason to expect amplified positive effects. So, when it comes to a real-life situation, the remedies that work so well in highly prepped animal studies may not work in human beings at all. Personally, I would argue that 8% of success in human trials account for similarities, while the remaining 92% of failures scream of fundamental differences between model animals and humans. Regardless of the true cause, these results cast a very serious doubt on the usability of animal models in translational research in general. Now, let's move to aging research. In addition to all problems inherent to translational biology, gerontology has its own skeletons in the closet. There are few animal models that gerontologists are particularly fond of, and these include microscopic worm called C. elegans and good old mouse, which I will use as examples. The model animals for aging research are chosen based on many criteria, including ease of maintenance in the lab, ease of genetic manipulations, and, above all, conveniently short lifespans. C. elegans is composed of about 1,000 cells, and its normal lifespan is around 3 weeks, and the mice enjoy a lifespan of 2 to 3 years. In aging research, an additional problem that reduces chances for success is that gerontology suffers from a particular kind of delusion that the aging process is similar in all species. All existing definitions of aging emphasize commonality of aging for all living creatures, which is true enough. At the same time, these definitions completely, and I would say almost deliberately, ignore fundamental differences of aging from species to species. As a guiding principle for research, the definition of aging is almost as important as 10 commandments. So, naturally, if the guiding principle is wrong, then most of the work may also be compromised. Because all definitions of aging are more or less similar, I picked up the first I stumbled upon on internet. On the website created by a good scientist, Peter de Magalhães, aging is defined as a progressive deterioration of a physiological function, an intrinsic age-related process of loss of viability and increase in vulnerability. Okay, sounds scientific enough. Now let's check how our model animals really age. Let's compare a few most agreed upon mechanisms of aging, including accumulation of mutations, free radicals, stem cells, senescence, and of course, telomeres. C. elegans acquires less than one mutation during its entire lifespan, which means that mutations have virtually no impact. There is also no input from the aging stem cells, and I'm not even sure whether contribution of senescence has ever been measured in the animal with a lifespan of mere 3 weeks. On the other hand, in most experiments, feeding C. elegans with antioxidants had positive effect on its lifespan, and this indicates that free radicals may play a role in its aging. It has also been shown that variation in the length of telomeres do not affect C. elegans' lifespan at all. In contrast, mice have a very strong contribution from somatic mutations in nuclear DNA. They accumulate close to 1,000 mutations per individual cell. Mouse aging may also have significant contribution from the accumulation of senescent cells and the deterioration of stem cells. On the other hand, the mice lacking active telomerase do not show any detrimental health effects or reduction in lifespan for at least 2 generations. This means that contribution of telomeres to mouse aging is rather questionable. As far as antioxidants are concerned, majority of experiments did not report significant increase in lifespan, which probably suggests that the role of oxidative stress in aging of mammals is negligible. Human cells also accumulate significant number of mutations, although fewer than mice. Similarly to mice, humans experience depletion of stem cells and progressive accumulation of senescent cells in many tissues. Large epidemiological studies fail to confirm life-extending effects of antioxidants. As far as telomeres are concerned, a multitude of correlational studies suggest that shortening of telomeres may be a contributing factor, although it is far from certain. Finally, human aging has a unique feature that is absent in short-lived mammals. At approximately 40-50 years of age, many human cells start accumulating enough mutations in mitochondrial DNA to render them unable to utilize oxygen and making them respiration deficient. So to summarize, the differences between model animals and humans appear to be pretty darn significant. We all age for sure, but our aging processes have different leading components. It is probably worth repeating that all mechanisms of aging are more or less operational in all species. Therefore, all available models are suitable for the analysis of the said mechanisms. However, there is a fundamental difference between model animals and us, which is manifested by significant and sometimes dramatic disparities in the relative contribution of various mechanisms to aging and lifespan. Recognition of these disparities is critical for the development of effective anti-aging interventions. because in all the universe of interesting things to learn about aging, we are truly concerned only about ourselves. Therefore, I would rephrase the original formula to reflect the species-specific reality of the aging process. Here we go. Aging is a progressive deterioration of physiological function, an intrinsic age-related process of the loss of viability and an increase in vulnerability driven by, and here's my addition, species-specific combination of leading mechanisms. If existing differences are acknowledged, then the efforts of thousands of scientists may be seen as simply misleading. For example, we probably know about aging of C. elegans much more than we know about our own aging. We have identified dozens of mutations that increase lifespan, sometimes dramatically. What we don't know is whether the newly discovered longevity genes and mechanisms have anything to do with our own longevity. Let's imagine that we manage to increase lifespan of C. elegans 100-fold to around 6 years. It would be considered an epic achievement for C. elegans, of course, but compared to the factual lifespan of human cells in our body, it would still be a failure. Please, don't get me wrong. The longer I live, the more appreciation I have for any form of life. I have nothing against this little critter, and I wish it well. It is just that human neurons in the cortex are as old as an individual, so they manage to live for several decades. Also, it is quite likely that most modifications causing extension of lifespan in C. elegans have already been utilized or discarded in longer-lived animals by Mother Nature. It also seems to me like hoping to improve performance of the tank through tinkering with the bicycle. Remotely probable, but practically impossible. As far as our aging is concerned, the only way we can truly make sure that the anti-aging interventions work is to test them on humans, and this would require decades, few generations of scientists, and many, many volunteers. The miracle anti-aging cures that are currently advertised are obviously not backed by any solid proof of efficacy in humans, and they rely only on crude theoretical assumptions and frankly idiotic testimonials like, I'm 50 and I feel like 30. Although irrational faith is bound to play a critical role in whatever you decide to fight your aging with, I urge you to exercise caution and due diligence. First, never trust any overly optimistic statement from anyone, including a president, a salesperson, or a scientist. In many ways, scientists are the worst, because they are so sincere in expressing their, as history invariably shows, misguided beliefs. Second, wait for at least 10 years after the first announcement of a breakthrough. The concepts that seem rock solid today are guaranteed to be challenged, heavily revised, or even disproved in 5 to 10 years. And finally, third, proceed with extreme caution, for there is always a significant chance that your trust in the name of yet another genius, a theory, or your own dumb luck is misplaced. To summarize, as the results of clinical trials show, there is less than 1 in 10 chance for interventions based on model animals to succeed in humans. With regard to anti-aging research, the chance is even slimmer because of prevailing perception that aging is essentially similar in all species. All of this means that gerontology has yet another problem, and that the currently accepted sequence, model animals to humans, for our search for the fountain of youth, is deeply flawed. So, what do we do? On this optimistic note, I'm going to wrap it up. See you next time.